All right, you ready? This is Top Job. Okay, great. Hi, I'm Joanne Coons. I've been a science teacher for more than 46 years, and actually more specifically an environmental science teacher. My students have been studying climate change, and as we investigate their causes and come up with hypotheses or ways or solutions for the future, I'm really inspired by the Top Job applicants because they're actually showing solutions that my students had dreamed about, and it's coming to fruition, and it's real time, and it's happening. So I'm really thrilled to see a very bright future. In conjunction with all the smart that goes into these Top Job projects, you can also feel the passion. You can feel the care of the product, which is the ground source heat pump, and you can feel that they really care about our earth and the people who give and receive the gift of clean heating and cooling. So this year's entries were all top-notch, top professional, top engineering and design. I would like to thank, wait a second. Okay. These are the Top Job winners. I'm gonna continue on. Well, I'm supposed to have the names of the, there we go. I want to thank the judges. They spent a lot of time and energy to review all the projects that were submitted. We have Kevin Austin, Matthew Damaris, Jack Deanna, Jennifer Livermore, and Jackie Shearer. So big thank you to them. I'd like to, let's see, backspace. I want to go back, but there we go. Okay. Okay, and now I'd like to introduce our Top Job winners. Okay, we have Matt Dennis from Halco. He is responsible for the Smith residence. It's a residential, we have, oh yeah, maybe I should say we have 3 different categories this year. We have residential, we have commercial, and we have drilling. We have Tony Amos from Endurant Energy, who did 55 Greenwich, that's the commercial. And then we have Johnny Fry and Eric Bosworth, who did the Framingham, or the drilling competition. I did want to say that all the entries, when we tallied up the points, they were just like a point or 2 away from each other, which means the quality of everything that was submitted was all excellent. But we did it very scientifically. We had a point system with a rubric, and we did it purely by the numbers. So these happen to be our top jobs. But kudos to everybody who entered, and really appreciate the time and energy they took. So we're going to start off with Matt Dennis from Halco Energy, and he is our residential winner, and he will show you his project.
Is my video going to play?
It should.
I don't know. Why don't you grab your mic?
We'll find out, right?
I can, and you have a clicker. Oh, yeah, turn that on, and here's a clicker.
That is the clicker. Hello, everybody. My name is Matt Dennis with Halco Energy. Real quick, Halco is a whole home performance contractor. We do everything that has to do with home energy and home comfort, from insulation and envelope improvements, anything HVAC related, air source, ground source, solar, basement waterproofing, water heaters, yada, yada, yada. So if it's broke, we can fix it. And if you don't mind, I'm going to sit and do this. As many of you know, I've been buzzing around here all day, and I don't stand very well.
I'm having trouble with your PowerPoint.
And we're having trouble with the PowerPoint.
So we're going to maybe, because we had to do it differently this year. Maybe pop it in right here.
Right here?
Talk amongst yourself. While they're figuring that out, I do like to point out when we do these, we are a proud GeoStar installer. This particular project is not a GeoStar system because GeoStar doesn't make what we need for this one. There we go.
I
Good?
can just click. You just tell me.
Okay, it's not going to work?
It'll work.
Oh, okay. Okay, so we are talking about the the Smith residence, named after Hal Smith, who happens to own Halco. This is his home in Newark, It is a, I'll come back to it. Obviously, it's a fairly old home. We're talking about 100 years old. It's a lot of history in Newark. It actually was the home of the, oh God, now I knew I was going to blank, right? I didn't put any notes. What's that? Oh, okay. I'm sorry. So I'm going to start off with a little video that we did, assuming it works, and it doesn't because the link's not on there. So hang on a second. Yeah, I put the link on there. I don't know, is that going to play? Should be YouTube. Oh, perfect. It's not showing up here.
Hold on.
Hold on, we got a video here.
And it's got a very unique history here specific to Newark, New York. The Jackson Perkins family built this house.
Perkins, I knew I
They started a rose business in the late 1800s. So they have a huge history here, and this was their home.
Yep, so I have to.
So the existing HVAC system in this home, so the home was built in
Sorry. So I just wanted to start with the video because this actually explains everything we did. This is a video we did with VP Supply and LG to show off the project. So
1910, and it's got a very unique history here specific to Newark, New York. The Jackson Perkins family built this house, and they started a rose business in the late 1800s. So they have a huge history here, and this was their home. So the existing HVAC system in this home was originally a coal-fired two-pipe steam boiler. So radiators throughout the house worked with heating. There was no air conditioning.
The plan eventually for this space is to operate as an event center, as a B&B. The LG VRF product specifically, it allowed us to really meet whatever changes were happening on the design side. If room layouts changed, the application of a space changed, we could change which indoor unit, we could change how the piping ran, and we were able to do that within the flexibility of the VRF system.
Well, most of the people that have a home of this vintage, they don't have the luxury of air conditioning. In our area, we've noticed over the last at least 10, 15 years, a trajectory of needing air conditioning more and more in the summertime.
With our future use of the home, of bed and breakfast, we obviously need heating and cooling in all the rooms, and the steam boiler system wasn't going to be sufficient.
Hal has chosen to install some clean energy that provides comfort as far as heating and cooling, cleaner energy, electrification. The challenge came when trying to keep it looking like a 1910s home. In order to convert these homes, we're evaluating the home with an audit. We have to do a more stringent design process so that we're making sure that we're putting the proper amount of equipment that comes in. And then all of your staff needs to be fully trained on this newer technology that's evolving every day.
For the LG design, we wanted to get every single room in the house heating and air conditioning. We wanted to have simultaneous heating and cooling. We wanted to have domestic hot water, and we wanted to tie it all together on one system so that the energy was shared amongst all of the indoor units as well as the hot water.
We're taking a pretty large home here. We're using an LG quasi-commercial system to try to tackle this project.
So there's a 20-ton water source VRF system. It's heat recovery. There's actually 6 heat recovery units throughout the home, and then 30 indoor units. It's 30 indoor units, 27 of which are in the actual house, and then 3 in the garage that turned into a few more living spaces as well. There's a lot of rooms in this home that are going to be occupied by different parties. They can control their own temperature, they can control their own mode, heating or cooling, whatever they want. They can turn the unit off if they want. They have domestic hot water that's provided off of the heat pump system. It's a full solution for an application like this.
These units are very quiet, they blend in, they actually fit in a lot better than a traditional air conditioner. They're slim, they're tall, they fit tighter up against the house.
Every indoor unit is a wall mount unit so that there wasn't any need for any ductwork, and they maintained as much of the historical and architectural value of the home as possible.
I switched all of my current business to LG, and we did lots of things to really insulate, air seal the home, make it heat pump ready, and then the LG products just fit perfectly. So it was a win-win for everybody involved.
Let's see if I can get this done. maybe it's that now. No?
Not so much.
All right. Get out of there. I didn't.
I'm doing that.
Okay.
Okay. All right. So, yeah, basically the video did a lot of the legwork for me here, but you know, as I said, it's an old historic house. It's a big house. You got 15 bedrooms. Forget how many bathrooms, but you know, the idea is the house is to be a residence and an event center or bed and breakfast. And most of the work we do is retrofit, and a lot of the housing stock in our market is old, so we deal with these challenges every single day. And there's more homes out there that exist than are being built new, so there's a lot more housing stock and a lot more opportunities to be done. Oh, that's fine, yeah. That's fine. And we took a whole house approach. You know, we insulated and air sealed everything we could to reduce the heat loss of the house to make it as efficient as possible. It's a tight village lot. I mean, I'll show you an aerial picture here in a minute. It's not very big. And Hal actually brought in three-phase electric into the house so we could do this along with some other stuff. And it's you know, it's a 20-ton three-phase VRF system with heat recovery, and I'll go a little bit more into that in a bit. Does heating, cooling, and domestic hot water. Like I said, challenges. It's a tight lot. Trying to build something like this, you know, a mini split style system in a house that only has radiators, doesn't have any ductwork. We weren't going to go tearing walls out to run ductwork all over the place. So what we did is we went with this the mini splits, and to try to keep it, you know, within the historical aspect of the house as much as possible. Like I said, existing two-pipe steam boiler, not really great for Geo with cooling. Wanted to do air conditioning. There's a high shot of it that's right before they started digging there. But we took out the boiler, which means we were able to actually use the chimney chase, took that out and actually made it an elevator, which is neat. And there's seven bedrooms in a previously unfinished, unconditioned attic, which is now completely finished. Spray foam the roof deck and the walls there. This is inside the addition that was built, but we foamed the attic space. Old lead windows, installed insulated interior storms. Again, the whole idea was how do we keep the look of this house without, you know, getting it crazy with modern finishes and modern fixtures. Obviously did a blower door test. I don't have a picture of the actual numbers because nobody decided to take a picture when they did it, but there was a significant air leakage reduction once we foamed everything. Here's a picture of the, I think this was right after we finished digging, but it's 20-ton systems, 3 separate loop fields, over 9,000 feet of HDP in the ground. There is a layout of what the ground loop looks like. There's actually 3 separate loops that are coming together. The main one is right there, and I'll show you in a second what it looks like now. And then we took out another one here. You can see the loop design. We've got, you know, stacked pipes on both. We had to dig down pretty deep. And the question is, okay, why didn't you just drill it? Well, we own the excavator, so why wouldn't you dig it? It's cheaper. There we go. So ground loop number 1 is the main loop right through here. The second one is down, it's like at an angle this way, and then the other one is going in this general direction. That is our excavator here for scale preferences, just to give you an idea how much space we're actually using up. But again, it's not that big for 20 tons to get into that space. And what did we use? So like Ben said in the video, it's a 20-ton VRF system with heat recovery, 3-phase. We've got 6 HRV units in the HRUs in the house, installed in the basement. 30 duct-free heads. They range in size from 5K to 15. individual controls for simultaneous heating and cooling, and that's the whole idea. If we're going to have a bed and breakfast, if we're going to have multi-use rooms, some people are going to want heating, some people are going to want cooling, and then of course we don't want to waste any of that. So with between the heat recovery system to do that, all that wasted heat that would otherwise be injected into the ground is also being used for domestic hot water. Those are the units themselves, 10 tons each. And of course, high wall ductless throughout the entire building. Every room has one of those. And that is the hydro kit that LG makes that you can tie into their three-phase product. And there's 3 120-gallon storage tanks. So that does 100% of the domestic hot water. There is no supplemental at all. It's all built in. The entire GEO system does everything. 18 bathrooms, that's what it was. I knew it was in there somewhere. And just for fun, that's not a very big space in the basement. As you can see the ceiling and the floor at the same time. It's barely enough room to get those tanks in there, but the guys managed to shoehorn all that equipment into a pretty tight mechanical room. In conclusion, Hal is very much put his money where his mouth is. There's a reason he did this. We took out a natural gas boiler and put in a pretty sophisticated geothermal system, lead by example. And he takes that stuff seriously, and he's very proud of this system when we finish it up. And the challenge we run into a lot of the times is trying to make geothermal work. Everybody talks about putting in geo. One of the things that, not overlooked, but a lot of the times, geo contractors overlook is is looking at the whole house approach and making sure the envelope is tight and the house is in good shape, because, you don't want to put a, high efficient geo system in a house that's not going to hold the heat. And, we take pride in what we do, and we hope that we can continue on and make everybody happy. And that's my spiel.
All right, so instead of jumping up and down, I'd like to introduce the commercial winner. That's Tony Amos from Endurant Energy, and he's going to speak about 555 Greenwich.
You found a laser pointer on there, didn't you?
All right, so while they're setting up, I'd like to encourage anybody out there with a project to think about entering next year, because this is really, also the, I guess he's done, but these projects and the other runner-up projects will be posted on our website. They're wonderful case studies, so please reference them.
Which one did you get for the green one?
Yeah, the green.
Yeah, good for you.
Cool. Thanks everybody, and massive thanks to the judges. I'll buy you a drink in the bar later. I'm thinking next year I'm going to submit my own residential property in the UK for an award. I actually learnt to drive a digger over 2 weeks, and I dug my horizontal trenches. But yeah, what a great project. But what it also means is that, all I hear about since I've been here in the US for the last 7 years, where am I going to drill boreholes? There are so many other options that need to be considered in those early stages of developing a project. And personally, I've been trying to drive the energy foundation option for the last almost, I hate to say it, 20 years. I'm kind of thinking, goodness me, where have those gone? Done a lot of projects in the UK, but I have to admit this is kind of one of the projects I'm most proud of. Hudson Square, 555 Greenwich, 270,000 square feet of commercial space, 17 stories, and what we've delivered here is kind of a great project. We had a great team to begin with. Heinz were the building owner, combined with Trinity Church, and they came together with a Norwegian bank. Norwegian, that's right, isn't it? Norwegian. Didn't sound right for some reason. And so they wanted to bring in a lot of European kind of heat pump technology and build an all-electric commercial space. So it's become the first all-electric commercial building in New York City. So you see the design team on the construction side. You see ourselves, Endurant Energy, our in-house design house, GeoOptimize, worked alongside Salas O'Brien to develop the energy foundation solution here. And again, what's really important about these kind of projects is that team work and coming together as a group, and not sort of fight one another and understand each stage of the work. So during the development, the Heinz team wanted the all-electric solution, so that meant heat pumps. And so we got contacted, and I said, we've got 120-foot deep foundations on this project. What do you think you can do? And what we came up with is we designed a system where we believe we could deliver about 40% of the building's heating and cooling. Now, Endurant Energy we never really design buildings to deliver everything from a geothermal system. It doesn't provide the level of resilience that you get when you combine solutions, ground source with air source heat pump. Now, I would suggest, and from the projects that we've seen so far, that a 60% ground source, 40% makes a good solution in terms of running a ground source heat pump. The Heinz team added a DOAS system to this, and even better, they then decided to go and utilize a thermally active structure. So every floor on the 17 floors has radiant floor heating and cooling, which is great when you start to connect those into heat pumps because they operate at such lower temperatures too. So you can see the geothermal loop. You can see the heat pumps on the left there. Loops being installed with the piles there, and then the thermally active floor slab. And what we've got here is a building that's delivering a big reduction in electricity compared to business as usual, 25%. And if they'd gone conventional here, they're saving 800,000 gallons of drinking water every year. Now, the building this gets connected to, 345, which is also going through a renovation, and they're putting in sort of water source heat pumps with energy machines. That building was using 4 million gallons of drinking water every year. That's one building in New York City evaporating that amount of water to deliver cooling to that building. Absolutely, yeah, it's drinking water. So the kind of smaller part of this, the new build, 800,000 gallons a year, and the measured carbon reduction we've achieved a 45% target there. No fossil fuels are being burnt on this site at all. So we kind of started off highly contaminated site. So again, drilling boreholes on a highly contaminated site, you're going to drag all that material down through into potentially lower aquifers. So again, you've got deep foundations being drilled. They're taking the material out of the ground anyway. But adding a geothermal loop to the foundations makes perfect sense because you've not got that additional drilling. So I'm just going to whistle through this a little bit fast. Just the highlights. Energy modeling, understanding the building's heating and cooling loads is absolutely crucial. There were numerous iterations because there was a lot of concern about how you model this type of building. So we looked at multiple options. But this becomes quite important once the building goes live, and I'm going to come on to that in a short while. So we've got the foundations. We've got 63 24-inch and 36-inch diameter piles going down to about 120 feet, large enough to put 3 geothermal loops in each of those piles. So then we kind of put that through our ground loop design software. So you see those 3 geothermal loops. Nothing is being changed about the foundations here whatsoever. So the geotechnical guys designed the foundations. All we're looking to do is to simply add geothermal loop to their design, the reinforcement detail. So again, it's that coordination, that crucial coordination in the design phase. But then, importantly, when it comes onto site, it's about coordinating with the foundation contractor. So we see our 63 piles here. We've got 3 loops in each. And again, it's all about resilience. So what happens if one pile when you're putting loops under a building, what happens if something breaks? So what we've got is 3 loops in each of those red dots. Those are the 24-inch and 36-inch piles. And what we've done is we've combined those 3 loops into a series, and each one is run back to a sub-manifold, which you see in those coloured rectangles. But then to add even more resilience to the solution, what we then do is we've got an east circuit and a west circuit. So there was a thought that maybe we could operate the one side of the building as a cooling system and then the other side as a heating circuit. So we could when you're delivering heating, you're chucking the cooling into the cooling zone, and then the seasons change and then you reverse the system. So again, energy modelling is crucially important, making sure that the ground isn't going to go out of control. So a lot of time spent on that. And here we are. I mean, there's the loop reelers, the piling contractors constructing the foundations here, and all we asked him to do was to lift the loop reelers into position once they had the reinforcement and they were ready to concrete this pile or grout it up. So as the reinforcement is lowered down, those geoloops are being added to that reinforcement cage. What's super important is you get the QA/QC right here. Flow test, pressure test at each key phase. So these are union workers. I'd wish they worked that fast. But what you see here is that, so you see the cage going in. There's a single bar on this one, but that larger diameter pipe is the Tremie pipe for grouting this up. And the plumbers that we had here literally they spent more time waiting for the piling contractors than there was no time waiting for us, basically. The only thing we asked the piling contractor to do was to put half moons in the spacer plates that you see in that middle picture. So the geoloops are nicely spaced around the circumference of the pile there. And then you can see the QAC flush test, pressure test at each key stage, super important. And one of the things I learned here was that HDPE pipe here is pretty bomb-proof in terms of abuse, getting abuse. And you see the machine breaking those piles down there, and I was quite concerned about it. But again, you know, the message here is coordination. Okay, if you damage the loops, let us know, because we can do a simple repair. And it's better you tell us about it sooner, because if you damage the loop at that stage, what we're going to end up with is material falling down the loops. And we don't want that. That's kind of like enemy number one. But what you're seeing here is that we then they trim the piles down, as you see in the bottom left. And then what we're doing is we're then connecting each of those piles and running them to the sub-manifolds through the existing structure. So there's no additional excavation for trenching and the horizontal loops. We're using exactly what's already being constructed to form the basement slab here. So that's a picture on the left on June 2021. Substructure complete, and what you see is tails. You see where all the sub-manifolds are going to be, so the sub-manifold on the right. But what we've done, every one of those loops has water in it, and it's under pressure, and if you zoomed in closer, you'd see we've got a pressure gauge on there. So, and what we asked, when we're not there, the site team check that the pressure's been maintained throughout on a daily basis. So yeah, then we're running the geoloops, all the horizontal loop, into a sort of like a subterranean cellar that was already there anyway for other utilities, so we just made use of that. And so yeah, you can see the false floor going on, main manifold. And that's what the main manifold now looks like, heavily insulated, before it runs up to the heat pumps on the roof. Now what I really like are these heat pumps. So these heat pumps will they can operate in either ground source heat pump mode or air source heat pump mode. So, and what's important is, okay, at what time do they operate in ground source heat pump mode and air source heat pump mode? So I'm going to come on to that in a little bit. So again, yeah, just a picture of the site, very muddy, you know. But what are the benefits of energy foundations? So what we're saying here, we're going to have no impact. We had no impact on the construction schedule here. There was no additional excavation works, no trenching, no other drilling rigs that would have been on that site, already congested. And again, we're kind of running those loops through slabs and beams that are already being constructed as part of the foundations. So this is the most important part of any geosystem, and that is the controls. Now, we were very lucky that NY-GEO also sponsored some additional monitoring, because one of the questions I get constantly is, okay, how do you know you're not going to affect my foundation performance? And I've had that question posed at me for the last 20 years, and there's a lot of papers about energy foundations, but what we've got here is some monitoring that we've also connected into the BMS system to help us make those decisions on whether we're using ground source or air source heat pump today. So we've got these thermistors and strain gauges for measuring the change in strain when we're heating and cooling. But we've also got, these instrumentation in 2 piles with geoloops in and 1 pile that doesn't have any loops in. So we've got a good sort of comparison in terms of what's going on. And we're measuring the temperature every 20 feet through the pile. Now, interestingly, the first pile there excavated, pile 4, I think this is, we did a conductivity test, so these are the results from that. But the first thing we realize is we've got a ground temperature of an average of about 70 degrees Fahrenheit. 70 degrees Fahrenheit. That's a classic example of thermal urban heat island effect. So, and we knew that the system was going to go live running into winter, so we thought, great, we've got a nice warm ground to start with, which is great. So the important stuff is the controls and the management and understanding what can be done when, a predictive control strategy. So the building's now been live for 12 months, and what we've been doing is collating a lot of data in terms of what the BMS is demanding, and we're comparing the actual building model with what we use in the design. That enables us to then recondition the building to the way that we want to operate it. And what we've created here is a thermal battery. So the target here is, in summertime, we want the ground under that building to be around 40 degrees Fahrenheit. And then in the wintertime, we want it around 90 degrees Fahrenheit. Because as you run into those seasons, we can then start to deliver really energy efficient heating and cooling. So right now, so that was October 2023 when we went live. So we can see, again, we've got that 70 degrees temperature. So we start heating, and we're kind of already going to start to drive that ground temperature down towards the 40 degree Fahrenheit target. Come February 2024, one of the coldest days of the year in New York City, you can see the temperature at the top here. It was about 24 degrees Fahrenheit. And what we're getting out of the ground is, I think it says about 55 degrees. And importantly, you know, if we'd have been using air source heat pumps at that time, the efficiency would have been 2.9, but those ground source heat pumps at 55 degrees coming out of the ground were operating at an efficiency of 5.7, a COP of 5.7. Quite clearly you can see the benefits from this kind of system. So moving forward, at this point we're cooling the ground down. The target is 40 degrees Fahrenheit, and this was April the 30th, and I think then this is July. So we're down at around. So we kind of started to trying to get the ground back up to that 90 degrees Fahrenheit. I think we're about 50 degrees here. But again, it's important. We're treating that ground like a thermal battery and getting it ready for the next season, basically. But the most important thing is monitoring what's happening with that system and looking at how you can improve it every year. Building use changes, we've got the ability to adjust. So first year data is ongoing. What we've seen is that energy model, that design energy model, being very conservative, which we would expect human nature. The algorithms that we've got in the system working well in terms of deciding the heat pump mode. And the energy foundations are certainly working very well and very reactive to what we're demanding of it. Now all that data is also being used to support education, Northwestern University, some good friends of mine at Northwestern University, University of Leeds. A lot of those people have all been trying to raise the profile of energy foundations in their own countries and things like that. So very important. Next step, education. And something that you guys probably don't know, but don't measure much, but what is the change in strain? And basically the conclusion at the bottom there is very, very small amount of change when we're heating and cooling the foundation. So again, that geotechnical guy is not going to be too concerned when we kind of show this kind of information. So, yeah, energy foundations. You know, there are a whole lot of other solutions. You know, so don't just think, where am I going to put those boreholes? Are you involved with a new build? If you've got very deep foundations, possibly this could be the right solution. Yeah, that's pretty much 555 Greenwich. That's been operational for the last 12 months. Thank you very much.
Well, next up, we have our drilling winners. That's Johnny Fry and Eric Bosworth, and they're from the Eversource Energy.
This guy, right? Is this good? Good?
Yeah, which this is the original.
You said this is the old one? Or? If it's on this thumb drive, I can open it.
Can you guys hear me okay? All right, awesome. So we are going to be talking about the Framingham Network Geothermal Project, and specifically drilling. I thought that it would be fantastic to have Eric Bosworth introduce the overall project and the challenge that was faced in Framingham, Massachusetts. And then I'll go through all of the key solution, value proposition benefits from a drilling perspective that we provided for that opportunity. In terms of introductions, I think Joanne said we're both from Eversource. I work for Celsius Energy. My name is Johnny Fry. I'm the U.S. country manager for Celsius, and we are a company that designs and builds geothermal systems. I also thought it was really cool to see we had incredible diversity up here, right? So, you know, Matt gave us a look at a horizontal ground loop. We had Tony going through the you know, energy foundation, energy piles, and we're maybe more focused on the old boring you know, bore field you know, installation in the subsurface, but we're looking at some cool inclined and vertical well placement solutions. So Eric, I'll let you kick it off.
Thank you, Johnny. So as Johnny said, my name is Eric. I am a manager of clean technologies at Eversource and have had the pleasure of overseeing this overall project kind of since site selection. For those that weren't in my earlier session, I'll just give a very brief kind of introduction here to the project itself, give you an overview, and then hand it back to Johnny. Essentially with this project, it is a utility-led thermal energy network. So we went in front of our regulators as a gas utility and asked to install a shared network in a neighborhood in Framingham, Massachusetts. And the idea was really to demonstrate that this technology is both applicable for utilities and really that's the right fit for these types of shared energy networks. When you're connecting up a bunch of private customers, residential homes, small businesses, large businesses on a shared network, the utility can bring a lot of value owning and operating that system and really providing that reliability to all of the customers, you know, within the neighborhood. So we were hoping to show not only that we could execute, but that we could do it with prudent costs and that this would be a viable business line going forward for our customers. So what does the project look like? On the right here, you can see a high-level snapshot. At its base, it's a 1-mile loop that runs through a neighborhood in Framingham, Massachusetts. It's an 8-inch HDPE pipe buried underneath the street, and we've connected up a number of customers, 22 residential homes. Those are single-family, duplex, triplex-type homes, 5 commercial customers, a portion of a large school, a cabinet shop, a fire station, a community center for the Framingham Housing Authority, and a small gas station. And then the balance were Framingham Housing Authority apartment units. So we hooked up 108 apartments across 9 different buildings to give us the balance of our load, and a really nice cross-section of all of the different types of customers that we as a utility would be typically serving. So with that background, I'll hand it back over to Johnny to hopefully go through some of the specifics around drilling and why we selected the Celsius solution for one of our bore fields. And just at a very high level, he'll get into a lot of the specifics on this, but we were looking for something that would leave us with access to the space that we were working in. We could provide that back to the schools for parking while we were doing the drilling. We needed to keep ourselves on schedule, on time, and then also allow available space for potential upgrades like a solar canopy in the parking lot that we were working in. And so all of those factors combined, when we evaluated the options, this specific deviated solution really made a lot of sense for us as a client, and it's why we chose to pursue it.
Eric, thank you very much. I think before I get any further, I think it's important to recognize all of the different collaborating companies, right, on this project. Certainly, as much as I'm up here speaking for Celsius Energy, it took many actors to make this project successful. That starting with Eversource, of course, Eric has already spoken. We can all appreciate how important they were to making this a reality. The City of Framingham, the Home Energy Efficiency Team, or HEAT, CDM Smith as the engineer of record, R.H. White, the construction manager, as well as, you know, from a borefield drilling perspective, certainly it was us as Celsius Energy, but huge thanks to Midwest Geothermal for work that they supported on this project as well. And last but not least, NREL and the Mass Department of Environmental Protection. All right, so just coming back to that challenge, right? Eric spoke to this a bit. I've tried to summarize this in 5 key bullet points, right? So ultimately there was 3 key bore fields, right, that were designed for service to these 140 utility customers, right, in Framingham, Mass, as connected to this 1-mile ambient loop. Within those 5 key targets, right, you'll see those 3 bore fields in a shade of orange, a shade of pink. You know, first and foremost, construct the bore fields now, right? Get this project delivered, get it executed. That was certainly common amongst all 3 of the different bore fields. Second was keep the sites clean, tight, and safe. That certainly is an expectation as well across, you know, all of the bore fields involved in this project. The last 3 items were really focused on this north parking lot, which was the largest bore field designed for this project. Taking a step back, this is a 375-ton project, so give you a frame of reference from the previous you know, presentations that were given. But ultimately, that north parking lot was designed as 60 vertical bores. Those bores were spaced at 25-foot spacing. And in light of that delivery, that was going to consume, right, basically end to end, right, the east and west, north, south, you know, limits of that available parking lot for execution of those installed bores, all of the associated trenching, lateral piping, so on and so forth. So the ability to go and deliver that while still offering the parking lot for faculty and student parking for the Mass Bay Community College was a key and critical consideration. As much as coming up with an alternative solution, right, to enable access to that parking lot, reduce the overall space and footprint for delivery, we had to make sure that you provided the same or better thermal capacity, right? You couldn't have a loss there, of course, and you couldn't also have some, you know, increased premium in cost. So how can we do it for same or reduced cost, same or better thermal capacity, but do it in a much tighter, cleaner, safer way? All right, so what was the solution? So I'm giving you a bit of a summary, and then I'll give you a bit more of a meaningful picture. But the solution was really a combination of approaches, right? It was continuing with a vertical grid or vertical borehole delivery solution at the 2 southern borefield locations. That's Rose Kennedy Lane, that's behind the fire station. These are 19 and 33 bore type installations. The space constraints weren't quite as critical at these sites. They were a bit more hidden, not as visible. And the focus, of course, on looking at our inclined pyramid solution, which is a unique Celsius energy delivery, was on that north platform, north parking lot. Here we installed 2 stationary drill platforms. That's very critically important, right? These drill platforms, one at the northernmost extent of the parking lot, one at the southernmost extent of the parking lot. Here we have the rig sit and for a 14, 16-week period operate in and amongst that individualized platform, drilling a number of inclined bores out in all directions, but staying isolated in that one spot, right? So not having to lift and shift and mobilize 25 foot every 3rd day, so on and so forth, right, throughout the execution of that drilling. On those 2 platforms, once again, one furthest north, one furthest south, you guys see the image in the pink square, if you will. We also had designed that inclined pyramid solution with same or better thermal capacity. We reduced those 60 original vertical grid bores down to a total of 35 bores, right? And that was done through significant sophisticated modeling, validation with the engineer of record, right, CDM Smith, reviewing and ensuring that, yes, we could bring 60 bores down to 35 by getting much greater well spacing and an improved completions configuration. So we moved to a quad loop or double U-bend assembly. We're getting 80-foot separation, right, on a per bore perspective as opposed to the original design of 25-foot spacing. We also implemented well trajectory control and as-built measurements. I'm going to say that again because I find it important. Well trajectory control and as-built measurements. Guys, we ensured that we delivered exactly what we designed, and we ultimately measured the placement of every single bore, fed that back into our very capable design software to confirm that we actually delivered that 375 plus tons that the project required. So, and then bullet points 4 and 5, and these were not unique to the north borefield drilling location. These were applied at all sites, but really to focus on keeping the site safe, and that was perimeter fencing around those drilling zones, ensuring that there was clear separation from the community and what we had ongoing. And then lastly was using diverters, right? Diverters and surface tanks for complete capture of drilling spoils, right? This is a incredibly important network geothermal pilot. You are in and among a very active community. Everyone can see the ongoing delivery of this project. That is especially true for this parking lot at the far north, Mass Bay Community College. I don't even know how many number of tours and visits, many of you in the room I'm sure likely even came for a visit, but it was literally a couple a week at times, right? So huge observation of the site. So keeping it clean and capturing all spoils, getting those into surface tanks and not dumping those to the ground was critically important. All right, so the picture on the right is really that finished result. So that's a top-down view of what those as designed, as built bores look like as they splayed underneath the Framingham Housing Authority buildings, underneath the Mass Bay Community College Farley building, if you will. This is this parking lot to the north, and even with extension under Normandy Road under additional Framingham Housing Authority buildings. So significant splaying out, once again allowing us to convert from a 60 bore solution to 35 and allowing us to install that on these very discrete and small centralized drill platforms that were stationary, not requiring the entire parking lot for delivery. Summary of benefits, I'm not going to go through all of these in great detail, but just focusing on a couple, right? So enabling us to construct the bore field now, keeping the site clean, tight, and safe, right, getting approval from Mass Bay Community College to construct during the school term, right, not having to wait until their ongoing school term was completed in December, but allowing us to start in that August timeframe and get working on constructing that system such that they could still, once again, use that parking lot for faculty and staff. The stationary drilling platforms and, of course, drilling zones, enabling 2/3 of the parking lot during construction. and then ensuring same or better thermal capacity, modeling and verifying with CDM Smith, who is the engineer of record, and verifying that through as-built measurements. On the same or reduced cost perspective, it's important to reinforce that this solution enabled a 74% reduction in surface piping and related groundwork. Right, we're able to deliver all of those bores, co-locate them in that, let's say 20-foot by 10-foot drill platform. It's the size of 2 car parking spaces. We're able to connect all of those bores together and not have these incredibly long piping runs, right, connecting north to south, ends of the parking lot for these 60 bores. So huge reduction in surface piping and related groundwork. There was already commitments and plans to basically, scrape and completely repave that parking lot for Framingham, Housing Authority for Mass Bay Community College, and therefore that was all scraped anyway. But certainly, if we did not have that preset commitment to go and repave the entire parking lot, this kind of installation solution would have further reduced costs by allowing you to patch back literally 90% less of the impacted or damaged space than what it would have been for that vertical well placement solution. And then lastly, 0% collision rate. Once again, with well trajectory control, we were able to install all 35 bores without a single collision. As many of you know, from a vertical ground loop perspective, collisions are unfortunately common. They should not be. But they can be anywhere from 10%, even upwards of 20% rate on collisions. So didn't have a single one due to impressive well trajectory control. I'll leave Eric to close on Beyond the Bore Fields. There's a lot more here on this project. Certainly thankful for being able to discuss the drilling aspect, though, and what we were able to offer as Celsius Energy. Thank you.
Thanks, Johnny. Just to kind of take a step back and also address this project, while we did demonstrate a great innovative drilling solution here, I wanted to highlight that the project itself had a large impact on the community itself. We had an environmental impact in pretty significant emissions reductions for everybody that were connecting up to the loop. There was a community impact, delivering heating and cooling to all of these customers that may not have previously had access to cooling, for example. And then ultimately there's a scalability question that we're trying to demonstrate here as a utility. How do we turn this into a larger business line and provide it to more and more of our customers? And it's important to note that we will be looking for innovative solutions like what we demonstrated here with the drilling as we go into more challenging environments. Dense urban areas, in our case that would be downtown Boston, Cambridge, Somerville, places where we may not have the luxury of large open areas for traditional bore fields. And so as we scale this approach and this technology as a utility, there's a lot of value in looking at what all of the options are out there for solutions to get a thermal network into a given area. So with that, I think we both just wanted to say thank you for attending the session, and it was a great project to work on, and I'm looking forward to the next one that we get to tackle.
Well, I can still jump up 3 feet. That's good. Okay, so this is a question, 4 minutes of a rapid-fired questions. You can raise your hand, and Matt will be around with a microphone. We got one right in the center. Go, Matt, go. Wait for the microphone, please, because we're getting recorded. Just state your name. Oh, yeah, sure.
Hi, Kevin Austin with Water Furnace. Hey, first a comment, congratulations to all 3 teams. Had the privilege of being one of the judges for this. And we had a wide range, very diverse, complex projects. And so your nomination and ultimate award was a really great achievement. So congratulations to that. And really just wanted to say thanks to each of you for participating.
Yep, congratulations to all winners. A little curious on the cone-shaped approach for Celsius team. How deep were the bores? You may have said it and I missed it, but.
Yeah, average depth was 720 foot.
720 linear, not vertical, but linear.
Is this working?
Yeah.
Measured length, yes.
Loop length, 720.
Loop length, measured length, 720.
That's impressive.
I have a question. I was wondering if we can get into the building code whenever you're doing a foundation, you could automatically put in a loop. How would we go about doing that? Makes sense, building ready.
Well, it's funny you should mention that, but last week I met up with Senator Kavanagh, Brian Kavanagh, and we kind of suggested exactly the same. So any building that's got new build with foundations, why not put a geoloop in it? It's just, every time I go to a JFK airport, I see steel tubes being driven in the ground down to 120 odd feet, and then they're just filled with concrete. So why not put a geoloop in them? So.
Now, I do like drillers, but that is a good idea.
So I also, can I ask a question?
Sure, go ahead.
So Johnny, what's the accuracy of your, when you got down to 720 feet, are you within 1 inch, 2 inch? What's the kind of accuracy of drilling?
I wish it was on the order of inches. That would be fantastic. But it's a perfectly good question. So over half of the bores that we installed were within 40 feet, right? So remember that we designed that at an 80-foot separation, right, at a minimum at that final extent. And please realize that these bores aren't all at the same exact inclination angle, right? So it's a nearest measurement, and those might be at different angles. So like this, right? So, but ultimately, yes, over half of them are within 40 foot, which is what we expect, right? From an overall delivery perspective, that would be on the order of 4 to 5%, right, deviation to that depth. At the very beginning of the project, we faced issues with the diameter and accuracy of the drill bits that we were purchasing, right? So many of those drill bits were ultimately, vast majority were under gauge, right? Some were actually over gauge, and that presents a critical drilling dynamic contribution that was leading to us having some unique build or drop tendencies that we worked through and identified as a bit supplier issue, engage with them on a QA/QC type perspective, got that resolved, and then we're able to nail the second half of our drilled wells within that 4%, 5% range.
Okay, it is 2:30. Isn't this when it's supposed to end? Okay, these were the presentations. The celebration is tonight, and I do want to thank everyone who entered, everybody who won, and the judges for their fine judging ability. So thank you. We'll hang out. Maybe you got a question. Come on up and ask it then. Thanks.
Thank you, Joanne.